A 100-watt light bulb has an efficiency of just 3%, which means 97% of the energy goes to heat. The bulb emits light with a wavelength of 500 nanometers. In part A, calculate the energy of one photon. So the formula for energy, in terms of the wavelength, is hc over lambda, where h and c are both constants, and when those constants are multiplied together, you get 1,240 electron volt nanometers, divided by the wavelength of 550 nanometers, so that the nanometers cancel out, and you're left with an energy of 2.48 electron volts. So that's one possible answer. You could also convert this into joules, where 1 electron volt is equal to 1.6 times 10 to the negative 19 joules, and you get an answer of 3.968 times 10 to the negative 19 joules. For part B, calculate the momentum of one photon. The momentum of a photon was given as h over lambda, where h is 6.63 times 10 to the negative 34 joule seconds. That's Planck's constant, divided by the wavelength. Since Planck's constant is in standard units, we have to put the wavelength in standard units also, so we've actually got to write it now as 500 times 10 to the negative 9 meters instead of 500 nanometers. And when all the units cancel out on that, you end up with a momentum of 1.326 times 10 to the negative 27 kilogram meters per second. For part C, estimate the number of visible photons emitted per second by this bulb. So we said the bulb has a power of 100 watts, but with the efficiency of just 3%, that means we're looking at just dealing with a 3 watts of power, which is the same as saying 3 joules per second. So in 1 second, there are 3 joules of energy. So the energy of one photon was hc over lambda, but for the full number of photons, which we don't know, we're going to just multiply this by an n, where n is what we're solving for. So the n, the number of photons, will be equal to E divided by, and I'm going to take this whole hc over lambda and divide by that, because we've already solved for that above. So E, the energy, is 3 joules, divided by the hc over lambda, which we also need to express in joules, which is what we solved for in part A right here, and that's 3.968 times 10 to the negative 19 joules. So the joules will cancel out in the numerator and denominator and leave you with a total number of photons of 7.6 times 10 to the 18. For part D, suppose the photons emitted per second were all focused onto a piece of black paper and absorbed. Estimate the force that all these photons, not protons, could exert on the paper. So the force, as we saw before in terms of the change in momentum, is delta P over delta T. That's Newton's second law in the more general form. The delta P is the momentum of all the photons, which there are n of them, times their momentum, and the final momentum is just going to be 0, so it's just going to be np divided by t. So the n, what we just solved for, was 7.6 times 10 to the 18. The momentum, which we got in part B, was 1.326 times 10 to the negative 27, divided by the time, which is 1 second, and that is equal to a total force of approximately 1 times 10 to the negative 8 newtons.